So welcome back. This is week 3. We're moving right along. In fact, we're doing these first 3 videos in one day here, trying to get ahead of our semester, because it should prove to be a pretty wild semester, producing all these modifications to our coursework. But anyway, this week we're going to be looking at the difference between average velocity and instantaneous velocity. And we're going to be using an inclined plane to do that. And you know, throughout all of history, you have these horrible instances where huge boulders roll down the mountainside and like crush houses. Or in this case, in Taiwan, we have this boulder that way up here at the top of this mountain, and during this rainstorm breaks free. So I'm just going to run that little video and you can see what transpires. This is a dash cam inside a car that picked up all this exciting footage. So here we go. There's no audio, by the way. You can see it's not up there anymore. Whoa! So that guy nearly got rocked. That is a big rock. Dang, that's a big rock. You know, I live on a few hills around here where there's some big boulders. It'd be so cool to see a boulder roll down one of these hills. And that's what you're going to study in lab today. You're going to look at the speed of an object as it moves down a ramp, changing, and then you're going to look at average speed. But we really want to use the definition of velocity. Just say we're going down a ramp with our rock, and that's the positive direction. So it makes it a lot easier. Let me go back just 1 second so you can see the rock break free at the top, and then we'll move to the next slide. Okay, so look up there at the top, and you'll see, boom, it breaks right free right there, and on down it comes. So anyway, it started from rest, by the way. Your lab, your rock, will also start from rest. So at t equals 0, the object will begin to move. All right, we need to see the spray of dirt again. I just love this scene. So he did get hit by some dirt, but he didn't get hit by that. Dang, the Lord was with him that day. All right, so let's go on to the next slide here. So anyway, in Greek mythology, there was a guy, a smart who really got on Zeus's bad side because he was so clever. He even pulled the wool over Zeus's eyes, and eventually he got punished. And for eternity, this guy's been rolling a rock up to the top of the mountain, and then when he gets it up to the top, having accomplished his goal, thinking that it's all over, the rock then rolls back down the hill and he's got to start all over. His name is Sisyphus. All right. So anyway, if you want to find the average velocity of something, what you do is you do this little calculation right here. You take a certain displacement and you divide by time. Now remember, displacement is a vector, so when you displace forward, that'd be a positive value, and if you displace backward, it's negative. And if you displace forward and then come back again, you see your average velocity would be 0 because you didn't displace anywhere. Now your average speed, though, would be different because you moved this far, let's say like 6 feet, and then you came back 6 feet. So you went 12 feet in like 12 seconds. So I went 1 foot every second. But velocity is a vector, and if your displacement is 0, your average velocity would be 0. So this is how you calculate average velocity. So now imagine in this picture right here, we have a ball on a ramp, and it's released from rest at the top and goes down the hill and gets to the bottom. And as it travels down that hill, I got the pointer right in my hand. So as it travels down the hill, my question is, what do you think the average velocity would be at that midway point right there? Well, there's an infinite number of answers to that question. How big of a displacement do you want? You see? So the goal would be, well, we want to find the instantaneous value of this ball when it gets right there. And so then we have to appeal to calculus. And you know, Newton was the person who first developed this whole notion of displacement over time, and then that average velocity becoming the true velocity if that time interval is chosen to approach zero. Okay? And we're going to do that in the lab. We're actually going to do that in the lab. And it's a pretty easy experiment. In fact, we're going to have, when you do it, you're going to do it at home, wherever you're set up watching the classroom activity. And we'll actually just have like one person in one house and another person in another house take two sets of data at two different slopes. Okay? And we'll pick 2 points, and we'll just split that up. So half the team can, say, analyze one half, their problem, and then 2 people in the other half of the group can analyze the other. All right? But your graphs will have both sets of data on it, so you could be able to compare what those graphs look like. Okay, so let's go on to the next experiment. The next slide. So, when we talk about instantaneous velocity, now if you look over here on the bottom, I could not find a GIF, because I don't know how to make a GIF. So I just stole this GIF off the internet. And it's a math GIF. So you know the x-axis is x, the horizontal axis is the independent variable, and then y is the dependent variable on the y-axis, but that isn't even presented on this graph right here. So what we really want is we want time, delta t, along the x-axis, and then x would be along the y-axis. All right? So it's x by t graph when we're talking physics, but when we're talking math, it's y by x. All right, so you can see in this figure right here, we have this point that we want to find the instantaneous velocity, the true velocity at that point. So what we do is we find the average as we get closer and closer and closer to that point. And you can see when I start way over here, the slope is almost horizontal. And as I go down, it gets steeper and steeper until it matches the graph at that point. In fact, that's the instantaneous velocity. It's the slope on an x by t graph when delta t goes to 0. And that's called the instantaneous velocity. So mathematically, it looks like this equation right here. So this is a vector, by the way, so there's a bold V right there. And the instantaneous velocity is the limit of the average velocity as delta t goes to 0. Because you remember, delta x over delta t on the previous slide was the average velocity. So as the average velocity as the delta t goes to 0, the average velocity will go to the true velocity, the instantaneous velocity. And so you can see down here, this would be x2 minus x1, the displacement divided by the time. So we can take that data, and we'll get a whole series of average velocities that get progressively closer and closer and closer together in time as they approach delta t equals 0. Now, here's the problem. It's very hard to change delta t. But it's super easy to change delta x in most situations. But if you use a video camera, you can actually do that. You can take the delta t and make it smaller and smaller and smaller. And in this picture right here, you can see you pick that point. This is x1. For you, it would be T1, okay? And then T2 would be somewhere, let's say on the right side right here. Okay? And what you do is you just find the delta x for delta t as it gets smaller and smaller and smaller, and then plot that ratio as a function of time. And time t equals 0 will be right here. So the time over here, whatever be the time it takes for that particle to get over at that particular spot, the curve. Well, we're going to keep it super simple. We're just going to go straight down a ramp, and it'll be very easy to keep track of the displacement and the time as we measure the average velocity and then find how it points right to the instantaneous velocity. Then you can see how it's tangent to the curve right there. You're actually going to plot the x versus t graph for a ball rolling down a ramp and then find the slope at that exact same spot that you measured it using the average velocity as delta t went to 0. First exposure to calculus as it applies to physics. And that's how it was invented, or discovered. I believe it was really discovered, because God is like the master mathematician. He just built all that stuff right in the universe, and we discover it as we go along. Okay, so we're going to wrap this one up. This is the background to experiment number 3, and we're going to talk about the experiment in the next video. So over and out. See you in a second.